All right, let's do another video here. So in this week's lab, we are looking at the kinetic and potential energy of two marbles that are rolling down two different tracks. And one of the things that the lab asks us to do is compute the kinetic and potential energies for both of them. And there's a good way we can help visualize that by creating graphs. So as to not deprive you of the pleasure of seeing what your actual real data is going to look like, I'm going to take data from a previous lab that you've completed, specifically the inclined plane lab, the one that we treated as frictionless, and doing a similar sort of analysis where we compute the kinetic and potential energy of this cart as a function of time, and then see what we can say about energy conservation. So what I did to start with is I just copied over the data from the Digitizer, and that's what we have here in these first three columns. So that's the first step, is putting it all into a spreadsheet. In one of my previous videos, I did everything in Excel. So here I'm switching over to Google Sheets just to be equitable and to see how it all works over here. And so everything over here on the right-hand side is just data from my analysis before, and I'll be recreating some of this because I'll need some of these quantities, but not all of them. So hopefully by now you have a good handle on starting from the time and the X and Y positions. Again, our time is measured in frames. X and Y's are both measured in pixels, and then we have to do a conversion to get to our values of time, our values of position, and then use that to compute velocities. So I'm going to scoot over here and slide back over to not ruin the surprise. And I'll sort of, all the analysis I already have done, but I'll sort of walk through where everything came from. I like to relabel these just to remind myself that these are in particular units. Each lab is not necessarily going to have the same frame rate and conversion from pixels to distance. This is something you have to redo for each of the video capture labs, but it's pretty straightforward. The FPS, frames per second, is just given as part of the lab, and then there's information given about how to convert from pixels to distance. So this is the inclined plane lab, and that was at 29.97 frames per second. And the width of the video was 87.5 centimeters, which corresponded to 1200 pixels. So creating new columns, and again, I just do this to remind myself of what my units are. Again, I can get the time just by taking whatever my time was in frames and dividing it by my frame rate. We notice we don't have to start at time equals 0 because the only thing we're going to be using is looking at differences in time. So I selected that, and I can copy it to all of my different cells. So as a quick note, I took data for every single frame. You don't necessarily have to do that for all the videos. For some of them, it can be handier to take data every 2 frames or every 3 frames instead. But for my inclined plane lab, I did it for every frame, and that will, and so I have 80 data points, and we'll come back and I'll talk more about these uncertainty numbers later. So the first part of doing this data analysis is going to be the same for all the labs. We have video capture. We're going to find our value of time, convert our positions as well, and notice that in this formula I don't have to separately compute whatever my conversion is. If I start with a number in pixels, I'm going to divide by 1200 pixels, multiply by 87.5 centimeters, and that gives me my position in centimeters. Same thing for Y direction. So those both have the same conversion, and again, I just copied that all the way down. And so my first set of data from the video capture is just going to be this time, X value, and Y value. For previous labs, one of the next steps has been computing a velocity, and then some later ones we go and compute a position. Our method for computing the velocity, we talked about this in a previous method, is by taking the values of the positions one cell up and one cell behind the given value of time. This essentially is computing the average velocity over this short 3-frame interval. So my Vx is equal to this distance minus that distance divided by our time interval, which is that minus that. And so that gives us a a more accurate measurement of our velocity over that interval. This is the so-called symmetric method. And then notice that we can't find a velocity for our first frame because we don't have any data before that first frame. And so I've blacked it out just to remind ourselves that we don't have any data for there. And again, copy that down. We would also not have any data for our last data point because again, we need one ahead and one behind. So those gives us our Vx's and our Vy's. And for this lab, the energy lab we're going to do, we are going to have to take into account both the velocity in the X and the Y direction. So when we move forward in this lab, it's going to ask us to find out the kinetic energy. And if you haven't gone and learned about what kinetic energy is, you're about to learn a whole bunch at once. It's just equal to 1/2 mv squared. It's a scalar quantity. And it depends upon the speed, which means that it's going to involve both the x and the y components. So again, Vx is the x component, Vy is the y component. To get the speed at any given moment, I'm just going to take the square root of Vx squared plus Vy squared, just using Pythagorean theorem. So again, in my formula, square root, and I just wrote, that cell times itself plus that cell times itself because it doesn't support the exponentiation operator the way we normally write it. Anyway, so this gives us our speed at all of these given points. And so again, copy that down to all of these different cells, and we have the speed at any given moment. And as far as energy is concerned, this is actually all the information that we're going to need from X, T, and Y. So sliding over, the next step is going to be we are being asked to find the kinetic and the potential energy at each of these points. So to remind ourselves, or maybe seeing for the first time, the formula for the kinetic energy of the object is 1/2 times the mass times v squared, and the formula for the potential energy of the object is m times g times y. Notice that for both of these, the mass is going to appear. And in previous labs, we weren't given the mass. We will be given a mass for this lab. The lab that you're going to do, these marbles are said to be 0.085 kilograms. And just for the sake of computing numbers and having them in the right units, I'm going to assume that the cart or whatever was undergoing this motion has that same mass. Again, the cart was actually more massive, but as far as energy is concerned, it's not going to make a difference. So a few other things. Notice that my potential energy is only going to depend upon the y value. So again, we have our y values here. That gave us our elevation. So our potential energy is going to be directly proportional to that. The other thing that we'll learn is that since we have the freedom to choose our coordinate system, we can choose the place where we say y is equal to 0. This also means we effectively can choose the point where our potential energy is equal to 0. And so down here, what I've done is, knowing that this 7.58 centimeters was the location where it started and that it only went up from there, I'm going to take that as the 0 point of my coordinate system. And so when I actually go to compute the height, when I compute this value of y, I'm just, for each of these data points, I'm going to subtract off this constant value. So, and notice I've created a new set of headers. This is because when I go to create my graphs, I want to have these labeled with the correct units. Notice also, even though time is still measured in seconds, my value of y and our speed, I've converted from centimeters to meters and from centimeters per second to meters per second. This is because I want to be able to write my energies in joules, which is my unit for energy. So, and again, I've shifted this down just to take into account the fact that we don't have these data points up here. And so the time values are just copied over. You can see it just uses the cell reference going back over there for my value of y. Something similar, we're going to use the reference we had back over here. Dividing by 100 converts from centimeters to meters, and then I subtract off that y0. So again, that formula gets copied down there. That then gives my height above that 0 point, or essentially my change in height above that initial level, as measured now in meters. Then I have my speed, which again comes from taking my centimeters per second and dividing by 100 to convert to meters per second. So we have our value of y, that's going to go into our mgy. We have our value of the velocity, that's going to go into our kinetic energy. So the next two columns are just using punching in that formula. So notice that I put the mass over here in a separate cell, just so if I need to change it or just to remind myself what it is, that 0.085. So when I set up my formula, I have 0.5 times the mass, which is in cell K4, and I use the dollar signs to make sure that that's an absolute reference rather than a relative reference when I start copying that down, and then I just multiply by v squared, which is the same thing as multiplying by v times v. So this now, again, copying it down, is going to give me the kinetic energy at every single point along that track as that mass is moving up and down the track. And again, you didn't necessarily have to put this in a separate cell. You could have just typed it directly in the formula. The only issue is that if for some reason the mass changes or you want to run this analysis again with a different mass object, then you have to go through and recopy all your formulas. For computing the potential energy, again, potential energy is mass times g times the height y. So again, I have mass that was in cell K4 times g, which I'm taking to be 9.8. Again, since we're in meters now, then it's just 9.8 meters per second squared, and then multiplied by our height y, where again, this is going to be the y minus y0. So in choosing where this is the point where my value of y is equal to 0, it's also going to be the point where my potential energy is equal to 0. And so maybe just to remind myself and to remind you, that's the location where our potential energy is also going to be equal to 0. Okay, so we have the kinetic and the potential energy for each of these different points. And then we also next are going to compute the total energy, or what we will call in the book the mechanical energy, which is the sum of the kinetic and potential, and that's just adding these two terms together. So as with always, if we sort of look at this big column of numbers, it's hard to sort of make any sense of it because all of them are different to a slight degree, and this is where creating graphs comes into play. So you can create individual graphs for each of these. So for example, by selecting time, let's say, I already have a graph made, so let me not select the whole thing, but I would select this. I'm holding down Control right now. So if I wanted to compute a graph there, again, Google Sheets is slightly different. I go into Chart, and then it gives me that weird thing, but that's not what I want because I always want to make scatter plots. Always doing scatter plots when we take this data. And not only that, but we don't have an x-axis, so we're going to put time along the x-axis, and then we're going to remove time along the y-axis, and this is going to give us a graph of what our potential energy is doing. We've only graphed this for a slight amount of it. We'll see the rest of the graph in a moment. But this is what our kinetic energy is doing. And I'm not actually going to keep this chart, so let's get rid of it. Delorted. Because it's actually handy to look at all of these quantities together in one single graph. And so to do that, again, I'm not going to select all the data, but I can actually select all three of these columns and put all of these curves into one single graph. So I'm going to go again, select chart, and then again, this is if you use Google Sheets, maybe you're getting used to this. I think it's a little easier in Excel, but it still gets the job done. You just have to know what you're doing. Again, I want this to be a scatter plot. I want the x-axis to be time, and I don't want time along the y-axis, so I will remove that. Now we get different behavior. And again, you can go through and add chart titles. That's over in the Customize area. Again, all of your charts should have titles, axes labeled, and both the x and the y axis labeled. But the idea here is that we can look at one quantity in one color, potential energy in red, kinetic energy in blue, total energy, and mechanical energy here in yellow. So we can see how all of them are varying together. So, like on the cooking show, where the host suddenly pulls out a completed dish from the oven, I'm going to show what this looks like for all of the data. So going from the beginning to the end, this is what our kinetic and potential energy curves look like. And this is the behavior that we expect to see, and so we're going to talk a little bit about that. Again, our kinetic energy was 1/2 mv squared. We were looking at the motion of a cart that started at the bottom of an incline, rolled up, reached a maximum height, and then rolled back down again. So at the beginning, all of its energy was essentially kinetic and virtually none of it was potential. And again, this is slightly above zero only because we had to ditch the first data point because of how we computed our velocity. But we start off with all kinetic and no potential energy. Then, as it climbs up the incline, we reach a point where it's going to come to a stop. Well, when it comes to a stop, that means it has kinetic energy 0. That means it reaches a 0 downhill. And it reaches a maximum height, which is why our potential energy is at a maximum. And then it goes back down again. Again, going down the incline means that the value of y is going to go down. So my potential energy curve drops, and then my kinetic energy is going to increase as it rolls back down again. So one thing to notice is that these curves are essentially just flipped versions of each other. And just starting off looking at the data, it might not be immediately clear why that has to happen. And it happens because of the conservation of energy. Even allowing for the fact that we have a little bit of friction, a little bit of air drag that's going to do work on this system. Notice that if I add these together, even though the kinetic energy is changing and the potential energy is changing, their sum really isn't changing by that much. And so my total energy remains a constant. And that's the whole idea behind conservation of energy. When you are constructing these curves for your marbles that are rolling down those two tracks, each of them will have a slightly different shape of curve going from kinetic to potential. But if you add together their kinetic and potential energy, then that should be fairly flat. And notice with all experimental results, it's not completely flat. There's a little bit of scatter here. So the last thing that we're going to have to do is talk a little bit about error analysis, and that's always fun. So I've talked a bit about that in some previous videos, and just sort of as a reminder, we're going to do it in terms of looking at percent uncertainties and fractional uncertainties. And the nice thing about that is because they're dimensionless, they involve the ratio of one thing over the other, they don't depend upon our units. And so we can actually just directly go back to our frame and pixel measurements to find out what these errors are. So, for example, if I'm looking at my uncertainty in time, right, because I'm measuring things to the accuracy of one frame, my uncertainty can't be less than one frame, right? Then I only know what's happening within that one frame. But then when I compute my delta t over t, I have to know sort of the total amount of time I'm looking at. And here I get that just by finding the maximum minus the minimum. That's going to tell me essentially the effective range of that. And so then my fractional uncertainty is going to be the uncertainty t divided by that range. So this gives me a fraction of 0.0125, or as a percent, just multiply by 100, of 1.25%. So, and we have an uncertainty in each of our directions as well. Again, this is going to be different for each lab. This sort of depends upon how smeared the image is. Notice as things start moving, they can get a little blurry. And so here, for this inclined plane lab, I felt pretty confident I could measure a point to within 2 pixels on either side. Again, plus 2 pixels or minus 2 pixels. So I took that as my uncertainty in the x and the y. For this lab, we had more motion in the x direction than the y direction. So in the x, we moved a total number of pixels of a little over 1,000, but in the y direction, it was less than 100. And what that led to, when we go and compute the percent uncertainty and the fractional uncertainty, our uncertainty in horizontal position is very low. It's less than 1%. But in the vertical position, it's very high, just because it didn't move that much in the y direction. And so that's our starting point whenever we're computing these uncertainties, is that we have uncertainties in the variables themselves. So remember these numbers, 1.25, 0.19, 2.22, because then if I go back over here, scoot down a bit, I'm going to start off with each of those. Then we had this method of adding percents that was talked about back in chapter 1, if I wanted to then find the uncertainty of any quantity that was associated with those variables. So the variables that we've introduced for this energy lab are Vx and Vy, again, the difference in position over time. So that involved computing things from x and t. So my uncertainty in that variable is just going to be my uncertainty in time plus my uncertainty in x. So just these two. And so Vx I can measure to with 1.44%. But my Vy, because that derives from y, and the y values had a much larger uncertainty, I can only measure that to within about 3%. So this gives me my uncertainties in Vx and Vy. However, we go one step farther, we're going to do more calculations when we compute our potential and kinetic energies, and each of those will also have their own uncertainties. Assuming that we can treat the mass as an exact quantity and we treat g as exact, then our fractional uncertainty in y is the same thing as our fractional uncertainty in our energy, because I'm just multiplying by a constant. So since we can measure y to 2.2%, then my uncertainty in the potential energy is 2.2%. It's bigger, though, when we get to the kinetic energy, not just because we are going to be involving all three of our variables, x, y, and t, but all of them are coming in squared. Since Vx is like an x over t, when I square it, it's like x squared over t squared, and this is like y squared over t squared. And in fact, t squared comes in twice. And so for the method of adding percents, when I raise something to a power, that then just gets multiplied. And so notice that when I go and compute these uncertainties, I have twice the uncertainty in my time, twice uncertainty in x, twice uncertainty in y, because each of them are coming in squared. And so that gives us an overall uncertainty. Again, this is just a measurement uncertainty of 7.32%. And so this would be the error I could report. Now, for this lab, we have something a little different in that we're trying to find out if energy is conserved, if my total energy stays constant. And it's easier to then look at statistically testing whether something is a constant. Because if I have enough data points, I can actually do some analysis on all these data points. So the idea is, if I look at just these yellow dots here, right, is this consistent with this quantity not changing? And if you look at it, you can sort of tell there's a little bit of a downslope to it. And that's expected because we do have some losses due to friction and air drag. However, to within the range of the scatter of the data points, it does appear constant. And so, in fact, since we have this whole column of numbers that just gave us our energy, we can use some functions. We can just take the average of all of those. So 0.0543, again, that's energy measured in joules. That would be this average value going through there. Not only that, but I can compute a standard deviation. If those of you have taken stats, you know the standard deviation. If you haven't, that roughly gives us our uncertainty or our error in that quantity. And so we're saying that this would be 0.0543 plus or minus 0.0016. This is the 1 sigma standard deviation. So again, converting that into a percent uncertainty, this means that this energy is constant to within about 3%. So it's interesting to note that I estimated from the uncertainties that my uncertainty in the energy is 7%. But the actual variation in the energy is less than 3%. And so we actually did better than what we had initially estimated for our error. And part of that is just because the method of adding percents actually overestimates the amount of error, and I might have overestimated the error in terms of how big these pixels are being smeared. From that, we can conclude that yes, energy to within statistical uncertainties is in fact conserved. If we had a percent uncertainty here that was much bigger than that, then we would have that was bigger than our percent uncertainty, then we will conclude that energy is not conserved. But since our actual error is less than our estimated error, that's fairly good evidence that it is. Okay, hope that makes sense. Again, your graphs will look slightly different because of the different shape of the track that you're using. However, when you compute kinetic and potential energy, you should see them add up to a number that's approximately constant. And again, you're going to have to do this twice, one for each marble, because each of them is following a slightly different track, but hopefully this gives you a good place to start. And as always, please fire off an email, go on the discussion boards if you have any questions. This is almost at 25 minutes, so I will stop recording now.